Again, this is the end of chapter 29. For a lot of you who are not live right now, and I've come basically notice that the fact that on Wednesdays we don't have as many people as on Monday. Anyway, this is recorded, so hopefully you guys who are not watching it live, you will follow with us. We have an exam on Monday, still scheduled for Monday. That's why we have to finish this chapter today. And I am hoping that everybody, whether you're live or you're watching this video recorded later on, that you go by the preparation of your exam as scheduled. The exam, the final format is not 100% decided. Honestly, it's probably not going to take as much time in terms of compared to exam 2. In other words, the allotted time will be probably shortened, but maybe more than exam 1. So it's going to be somewhere in between. So this is basically in a nutshell where we stand in terms of the exam. We have a bunch of stuff that is due this weekend. We have homework, we have labs, we have so many things that are due. Also, I recorded the instructions for the lab, for the E/M lab, and I posted it on the instruction itself, basically on the lab instructions, the lab basically assignment itself. I posted, I think, less than 15 minutes instructions on how to do the lab. If you have difficulty with the lab, please do ask. Do not keep it. It should be self-contained in a sense. It should be easy to do if you guys follow the instructions. But if you have difficulty, please let me know. Okay. There are some questions in there. Basically, all you have to do is sub the values of V. There is a condition for V. They didn't go and discuss it, and that is that the velocity need to remain about 10% of the speed of light, because these electrons, when they come zooming with tremendous velocity. So we want to make sure that the physics we're using is valid. In a sense, we're using classical mechanics, and that classical mechanics still gives us the results. Now, if the velocities are higher, because these electrons are super light, then we have a problem. Then this mechanics won't work, and then we have to invoke other mechanics or physics. But at this point, we're assuming that all the velocities that the electrons merge from this experiment are below relativistic values, and then the experiment would work. So I would urge you guys to go through the instructions, go through the video, and if you have difficulty or questions, please let me know in terms of the lab for this week. It's due this Saturday. I'm sorry. So you really have to get going on it as soon as possible. In terms of the lecture, we still really have a couple of technical issues that we really have to address, that we have to, not technical issues, what should I call them? Basically, two key concepts that we have to address. And once we pass that, we should be ready in terms of the concepts. Okay, don't forget that we also have a quiz for this part 2. Okay, so that covers chapters 27, 28, and 29. So let's go quickly through the things that we have so far, where we stand. Let me share with you this screen. And so this is the concepts that we did so far. We explored the Faraday's law, and I think we went through it in a little bit of detail in terms of how it works, especially the sign issue that I emphasized that it is probably the most important one in terms of calculations that you really have to pay close attention to it. Now, there are a couple of concepts that we need to get to. One of them is actually the power generations for the AC current, because Faraday's law turned out to be the law that we use to create current, to generate current to our households or the industry, the AC current namely, okay? And that's one thing. The other thing also, we're going to summarize everything we learned so far. And that is, and we will discover that there is something the matter with Ampere's law. And Maxwell actually went in and fixed it, and that should be basically the concepts that are going to be testable at these concepts in this chapter. Okay, so let's get going. Let me see if I can add a new page. And the first thing in terms of the power generation. So imagine with me, you have the following scenario. You have a magnet, okay? And this is the south pole of the magnet, okay? And then you have a north pole from the other side, basically, facing it. So this is a magnet. And what you do in this case, you take a loop. Going for the sake of argument, draw this loop as a rectangular shape, okay, of a wire. Okay, let me draw it with a different color because I think it's kind of confusing to draw it with the same color. So let me pick up the blue color in here. So this is my loop. This is a conductor, okay? So think of it that this is copper, for example, okay? And from here, you're going to take two leads, okay? And the leads, they're connected to brushes. So the technical details involve a lot of stuff in here, okay? And what you do in this situation, you manually turn this, okay? You give it an omega. So you have a rotation per minute or per second or whatever that is, okay? That is going to be critical to later on determine the frequency of the signal, okay? So this is a design issue on how to rotate it. So think of this one that you have a wire, a bunch of wires actually. What is it? Connected together, and you turn them, and you can have, for example, the water as it's falling, it's going to turn them, and as this one turns, now you have a wire whose area now is this one. So this is the area of the wire, okay, A, and it's spinning, it's turning, okay. Sometimes this is the direction of the magnetic field, by the way, I didn't draw that, but you should know that the field is always pointing from north to south. So this is a B field, okay? And the B field, and in this case, the area, and since I made it spin this way, so my area has this value. So I'm going to take it in the positive direction, okay? I really don't care for this direction to be. So think of it, tilt it a little bit. So this is the area. It's perpendicular right now to the surface, okay? So the dot product now, in order to find the flux of the magnetic field, the flux of the magnetic field is supposed to, B is constant, so it's going to come out of the integral. Technically, this is the flux of the magnetic field through this area. Phi is equal to the integral of B dA, okay? But from this geometry, clearly B is constant throughout the entire region, okay? As long as I don't move my magnet. So B will come out of the integral. Furthermore, this dot product will involve B times dA times cosine of the angle between them, cosine of theta, okay? A, the area in magnitude itself, is constant. The area is just the width times length. So the only thing that changes in time, really, okay, is this cosine theta, because theta, I made it sure that it spins with an omega t, okay? So this is the angle theta in this case, because I'm spinning this one at a constant rate omega t. For some reason, I spun it in the wrong direction. Usually we spin it in the positive direction counterclockwise, okay? So fix the direction in here. So it's being spun in this direction. So in this case, the area, so that's what gave me the headache earlier with the sign issue, okay? Anyway, if it's just a negative, just shift the whole origin of the system and it's going to be fine. So the sign in here doesn't matter because it's just the magnitude of what's going to come out next, okay? So here is the, that is coming from the dot product because this is a dot product. So at the end, it's B times A, the flux, because B is constant, everything is constant. The only thing that is changing, and it's changing in time because this integral is in space actually over the area. So this will come out of the integral also. This is coming out of the integral. So the only thing is left in here is the B times the area. That's it. B times A times cosine of theta. Okay. So this is the flux of the magnetic field. Now, if I want to apply Faraday's law, the EMF now that is generated in here, in other words, I can connect this one to a light bulb if you want to, but there is an EMF in here that is going to generate, and the EMF is going to be minus, and again, we really don't write the minus until toward the end, because again, the that's Lens law, okay, how to find the direction of the magnetic field. So it's going to be just minus BA times omega times the sine of omega t, and remember, the derivative of the cosine will bring me also a negative sign. So in other words, the derivative, so this is basically what I was taking derivatives with. Let me take it step by step, because sometimes making too many steps can bring confusion. Okay, so this is basically what I'm taking the derivative with respect to of B times A times cosine of omega t. Obviously, the derivative of cosine omega t is minus omega times sine of omega t. That's with respect to time. And I already have a minus in there. And as I said before, you really don't need to worry about the minus that much, because at the end just tells me which side is positive and which side is negative. It tells me which side is going to be basically the positive side and which side is going to be the negative side. But because the sine omega t will change, this is a periodic function. So this is going to switch polarity. It's going to go back and forth between the two sides. So the signal that I'm going to get, or the EMF that I'm going to generate from it, is B times A times omega times the sine of omega t. This is a periodic function, okay? So you say, okay, can I make a sine equal to cosine? Of course. All you have to do is wait about 90 degrees and start your rotation. So instead of saying from here it's cosine of omega t, you're going to say cosine of omega t plus pi over 2, and that will bring you to a sine, and derivative of a sine is a cosine. So in other words, in general, the signal has a phase in it, okay? So that is basically, that depends on when do you start time, when you start the clock. That's it. That's when you click on the time. Maybe it's already spinning, and right after 5 seconds you start the clock. Then at that time you don't say it's cosine of omega t. It's cosine of omega t plus t naught. Okay. So it's just shift the origin of time, and you can choose omega t naught to be specific values like pi over 2 or any other phase for that matter. So that depends on the choice of time. What I did in this situation here, I chose time to be exactly when we started spinning this one. So if that's the case, then it's a cosine of theta t. Otherwise, in general, it's going to have a phase in it. And since it's a phase, I'm going to have the signal in general. This is going to adjust the maximum value of the voltage in here. So this is going to readjust, because this is an EMF. So this is going to be some maximum value times the sine of omega t plus some phase. Don't confuse the big phi, which is for the flux of the magnetic field, with this one. So now I have really a power source, okay? If I connect this one to a resistor now, if I connect this one to a resistance, now I have a current running through the wire. Using Ohm's law, I can actually find if I have a resistor R, then I can find the current in the wire is going to be, again, the EMF over R. And the EMF in here is Vmax over R. Times, of course, it's time dependent. So the current that we receive at home is alternating. So this is an alternating current. It changes from positive to negative. And this is basically what we mean by an AC current. Alternating current. And if I want to represent the voltage in this situation, this is how it looks like. I took a phase, so it doesn't matter where I start. So it could be here, maxing and coming down. So in general, it's a periodic function, okay, that goes up and down. So this is the EMF, of course, as a function of time, and it's a periodic function. This is how your AC current look like, okay? In the case of the resistor, all you have to do is apply Ohm's law, and if you only have a resistor, so that is how much current is in that circuit. Now, it is interesting to try to find the power. The power, you guys remember, we said it's the voltage times the current, and the voltage in this case, it's the EMF across the resistor times the current, and the current in this case is actually the EMF divided by R. Okay. Another way of writing this one is epsilon squared over R, and the power then is going to be given by the expression of Vmax squared over R, and times the sine squared of some omega t plus some phase. Okay, if you want to make it easy on yourself, you can again choose the origin of time so that this phase is 0, but you don't have to, okay? So this signal now looks like this. This is the power now, how much it's consumed in a wire, in a resistor. So at some point, it's going to be positive, and when you square a positive, you're going to get a positive. And sometimes the signal is going to be negative, but when you square it, it's still going to be positive. So in this second side, when it's negative, the signal is still positive. And when it becomes positive again, when you square it, it stays positive. And when your signal becomes negative again, so across the resistor, always the consumption of this power looks like it's above the x-axis. So this is power now. We're not talking in terms of current or voltage or anything. Voltage go up and down. So the voltage across the house in here, it's going between some V max and some V min, between the two. But if I connect it to a resistor or any device for that matter, it should give me a current, and the power is going to be always positive. It cannot be negative power. And that's clear from this expression. Okay? Now I want to find the average power for every cycle. Okay? Because this is a periodic function, and the periodic function in this case is actually the period of it is 2 pi over omega, if you guys remember from physics 4a. So the actual signal itself has a frequency, or has a period of 2 pi over omega. This is from physics 4a. Okay? So I want to find the average power consumed in one period. Okay? So what that would go then, P on average in one cycle is going to be, we're going to define it just as adding from 0 to t of all of the power as a function of time. And of course, since I'm going to have, so of course time is dt, I'm going to integrate this expression, I'm going to divide by the period itself. At this point, I don't know what the period is. I just throw it in there because I don't know what omega is. But I know what this value is in relationship to omega. So again, I'm going to integrate this expression with respect to time from 0 to the period, and then divide by the period. So this is the average over a cycle. So this is average power over one period. So you sum from 0 to the period, and then you divide by the period itself. That's what we do when we find averages. We sum from some scale and divide by that scale. Now I have an average. Okay. So this is by definition, if you wish, the average in this case when I have time dependency. So again, I'm going to throw the value in here for P, for P, yes. And it's the integral from 0 to t of V max squared divided by R, and those are constants. The only thing that is not constant is the sign in here. Okay, times dt, of course. This one comes out of the integral, the R comes out of the integral, and I have to use an expression in here for the sine squared. There is a formula that you guys have remembered. If you guys remember, we had it a long time ago, where we say that 1 minus 2 times sine squared of anything, okay, is equal to cosine of twice of that same thing. Okay, oops, twice of that same thing. Okay, so I'm going to apply it in here where that thing happened to be omega t plus phi. So sine squared then of omega t plus phi is, per this formula, if I move it to the other side and move this one to the other, that side, it's going to be 1 minus cosine of the same argument, which is cosine of 2 omega t plus phi, plus 2 phi in this case, divided by 2, because I have a 2 in here. So I'm going to replace it in there and do my average, because it's easier that way. So my average power consumed over one cycle is going to be, again, V max squared over RT, the integral from 0 to t, and I have a 2 in here in the denominator, so I'm going to take it out, and I would be left with 1 minus cosine of 2 omega t plus phi. 2 phi, that is, and the whole thing is integrated over dt. The integral of 1 is simple enough, which is just 1. From 0 to t, it's going to give me t. And the integral of a cosine is just a sine divided by the argument of the, so this will give me actually negative, because I have a negative in here, okay, 1 over 2 omega, the sine of 2 omega t plus phi, 2 phi. And this is evaluated between 0 and t. So I'm not worried about this one yet, okay? I want to know how much this one is. For big T, this is going to be sine of 2 times omega times big T plus 2 phi. And for 0, it's going to be sine of 2 phi. Well, omega times T, capital T, is just 2 pi. And multiply by 2, it's 4 pi. And we know that sine is a periodic function. It doesn't matter if you add 2 pi, 4 pi, 7 times 2 pi, that is 14 pi, or negative 2 pi. It's the same thing as the sine of the other argument. So this actually is the sine of also 2 pi. I'm subtract from it sine of 2 pi. So the upper limit and the lower limit are the same, and they give me 0. And that is because the cosine is a periodic function. So if I'm going to have one value integrated, so it's going to give me the average. Sometimes it's positive, sometimes it's negative. It's going to cancel out on average. So this is 0. What remains is the integral of 1, which is just t, evaluated from 0 to big T, which is just t itself. So what is left in here for the average, P average, is going to be V max squared divided by 2 times R times T times T. So the T and the T cancel. And this looks like this, V max squared over square root of 2 squared divided by R. The reason why I'm writing it this way, because this looks like it's an effective voltage divided by R. So P bar looks like some voltage squared divided by R, and this how it looks like in a DC circuit. That is how much power is consumed. So the AC circuit is equivalent to a DC circuit in here if I don't have, if the voltage has an effective value called the RMS actually, which is simply equal to the maximum value divided by square root of 2. In the United States, this value, the RMS value, is 120 volts, which means that the Vmax in the United States is 120 times square root of 2. So in the United States, the maximum voltage is 170. So the voltage fluctuates in the United States between 170 and negative 170 between these two values. Okay. On average, it's as if it's working at 120 volts. Okay. Effectively, this is how it works. Okay, with this expression. So from now on, the RMS stands in here for root mean square. Root mean square, because this expression is, you can get it from here by taking the root of the mean of the square. Exactly, that's what the words one by one in this order too. So what you do, you take the sine and you square it, and you take the mean, which is just the integration. That is what the mean is, and you take the root. So it's the root mean square. Okay, so that's why they call it the RMS. So when you read about the RMS, this is exactly what it is. It's telling you what to do, and that is how you find the effective voltage. So that's basically one thing. The other thing I need to mention in here, in the United States, omega is equal to 2 pi times 60, because in the United States, the frequency is 60 hertz. If you happen to go outside of the United States, they use a different frequency, and that is basically 50 hertz, and the rest of the world in the United States, they use 60 hertz. So that is omega. So omega is 120 pi. So that is the value that is used in the United States for omega. In the United, and the rest of the world, it's 100 pi's. So that is something that you have to, in the rest of the world, they don't use 120 volts. They use 220 volts. Not the rest of the world, not everywhere. I think there are some places in here, like, for example, in North America, like Canada or something else, where they use different voltages, like 120 and things like that. But the thing to remember, so if they don't tell you otherwise, if you're plugging it to the wall, they tell you it's 120 RMS, two things you have to remember, okay? If they tell you it's in the US, you can assume it's 120 volt. Then if they're asking about the max, then you have to multiply that value by square root of 2. That is if the signal is periodic, because sometimes if it's periodic and it's a cosine, harmonic function like a cosine. But if I give you a different signal, like for example, this signal is going to increase and then shut off, and then increase and then shut off, and then increase, then shut off. Obviously, this is periodic, and the period is this time, okay? And it repeats every period. So if I'm going to find the RMS again, I'm going to square this value and then basically average this one. Or I can give you another signal that turns on and off by itself, like a square signal, and then it's shut off or goes to actually a negative value, okay? and then it's going to be positive for half a cycle, then it's going to be here, and so on and so forth. Obviously, the period of this signal is from here to here, okay? And I have to, again, find the average for this signal, okay? If it's always positive, it's still from here to here, because for this cycle, it's 0, or half a cycle is 0. For this half cycle, it's a positive value. Again, the signal can be, this is a square signal. So as you generate your signal, it doesn't have to be a sine wave function like we did earlier. The root mean square is the same function in here for all of them. You have to square the signal. Doesn't matter, positive or negative. You're going to square it first. You find the average, which is just one of the period integral from 0 to the end of the period, and then you take the square root. RMS. R for root, M for mean, S for the square. Okay. You square first, you take the mean second, and you take the root second. There is a lot of questions in here. Does the mean of the squares is the same thing as the root of the this one? No, they are different, and you can get into more statistical effects, and you will see why that is. Does this make sense? Do you guys understand the power generation, especially in the case of the United States, how it works? It's all based on Faraday's law. It's all based on this law, actually. You find the flux. You take a wire, you spin it in a region where the magnetic field is constant. The wire shape doesn't change. So the area A is actually fixed in terms of the geometry. What changes in here is the angle between A and B, between the area and the magnetic field. And that is constant in space. But what changes in this case is the area, the direction itself only. So you take that out of the integral, but it's constant over the area, okay? So at a given configuration. So you take that out of the integral and you're just left with B times A, because B is uniform in this situation. And then you apply Faraday's law, and now you have an AC signal. This is how power is generated everywhere, not just in the United States, but everywhere. And you can use, for example, the falling water to spin your turbines, and then you have power. Or you can actually use a diesel engine or whatever engine you can have. I mean, or the pedals also that you're pedaling on your bike, you have a dynamo there, and I don't know if you have that on your bikes or not, but that also generates power so that you can see the at night, and you have a flashlight in there. I know some of the new flashlights, they don't use that, they don't use the pedal, but use just a flashlight with a battery. But that's basically in a nutshell how this power is generated. And now you have an AC current, and this is the essence of AC current. AC current, because they are changing, but you can have them behave as if they are DC current, so effectively as if they are DC current by just finding the RMS. Does this part make sense to you guys? The ones who are present, of course. I strongly suggest that you guys review the content if you have difficulty with it, or please let me know, okay? Can we continue? Okay. Okay, very good. Thank you, Daniel. Okay, so the next topic in here, which is the summary of everything, okay, that we learned so far. When we met way back in August, and it sounds like it's antiquity, but it's only 2 months ago, okay, we said that we learned from physics for A, F equals to ma. And I promised then that we're going to discover a new force, okay? If we find that force, we're in business, basically. And we introduced it via Coulomb's law. And we said, instead of defining it into Coulomb's law, let's define the electric field. If I can find the electric field due to any distribution, and I can apply this law, basically, by definition of the electric field, to find this force, and now in business, back to physics 4A, way back in the chapters 4 or 5 or whatever, when we started with the physics, okay? Again, I did not teach you physics 4A, but I think that you understand the logic behind it. Now, so we have that force defined by the electric field. Now, the electric field, of course, is produced by, it could be produced by charge or distribution of charges. And the way to find it actually was via Gauss's law. Gauss's law says that the flux of the electric field, which is basically this value, again, this is phi of E, not phi of B, because now we just discovered the new flux, over a closed area that's what that circle means, is simply equal to the charge enclosed divided by epsilon naught. So if somehow I can find the charge enclosed and argue the symmetry in this case, I can find the electric field, which brings me back to the first point, and now I'm in business back to physics 4a. Okay. Another way of writing, so this is Gauss's law. This is really the biggest thing that we discovered in the beginning, okay? Then I did not argue this, but the mathematics should not be hard enough to argue, and I hope that you guys are going to do vector analysis, vector calculus, where you can show that this is equivalent to saying that the divergence of the electric field in a specific point in space depends on how the charge is distributed in that point in space, which is rho divided by epsilon naught. So these two expressions are equivalent. This is an integral version, and this is a local version. The reason why this is true is because this integral in here, you can write it as 1 over epsilon naught, the sum of the charge enclosed, is the integral over the entire space enclosed by that surface. So this is the volume enclosed. I'm going to give it a name so that's area A, okay, by A, okay, of rho dV. Then you use actually a theorem in calculus that takes this double integral and brings it to a triple integral, and since this is true all the time, then the integrands must be equal, and this actually will involve the divergence, and that's how you prove this theorem, okay? So that's basically the first law that we discovered. Again, that gives me, if you wish, the electric field in that situation. Then we discovered magnetism. Of course, the electric field turned out to have a property which was it's actually how should I find the word that's escaping me? It's produced, not the produced. Oh man, this expression, the potential, derives of a potential. So the E field in this situation derives of a potential, okay, electrical potential. That's what allowed us actually to get into circuits later on. We were able to get circuits, Kirchhoff's rules, and we were able to do all kinds of things, and we were able to do capacitors, many things after that, just based on these two concepts. Then we discovered magnetism. And magnetism from the get-go, since there are no monopoles, we know that the flux of the magnetic field over a closed area, any closed area in this case, any closed area, is going to be 0. Why? Because there are no monopoles. Okay? The reason why this magnetic field is important is because when I have magnetism, this law needs to be modified. I have to add to it the effects of magnetic field, which experiment has shown to be given by this expression. So now I need to know that the magnetic field also is. So knowing the electric field by itself is not going to help me go back to physics 4a. So I need B also, okay? So we know from the get-go that the magnetic field has no flux, at least over closed area. It has it over an open area, but not over a closed area. Closed area because there are no monopoles. So at the end, you will have the magnetic field will come from a region and will end back to it. So if the area is outside, it's going to give me 0 no matter what. But if it encloses the magnet, the fields that leave will come back. So at the end, I tally 0. Now, this expression, similarly, mathematically, equivalent to an expression with a divergence, that means the magnetic field does not diverge. It's always 0. So the divergence of the magnetic field is always 0, similar to the previous one, but except now I don't have any monopoles. I don't have magnetic charges to add them up or say how much they're distributed or anything like that. So these are equivalent. So I'm writing it in differential form and integral form. So this is the fact that I don't have monopoles. This is Gauss's law, if you wish, for the magnetic field, okay? Now, we discovered Ampere law, but I'm going to delay Ampere's law for a little later because I'm going to go straight out to Faraday's law. And Faraday's law says that the rate at which I'm going to put the minus phi at first and the derivative in here of the flux. Now this is open, so this is an area that is open in space, okay? Because if it's closed, we're back to zero again. Of BdA, this is basically, again, the flux of a magnetic field over an area, is equal to the circulation of the electric field on a path that encloses this area. So this is a path, this is an area enclosed by that path, by the path. When I say the, I mean this one, okay? So this is basically Faraday's law, Faraday lens, and I need the word lens because of that negative sign, okay? So in the differential form, this still resolves to basically a minus, because I'm going to have this one in double form, and I'm going to integrate and then equate the integrand. So it's going to be actually the partial of b with respect to time. Okay, and on the other side, this would be promoted to a double integral over the same enclosed area, but instead of doing E, we're going to do curl of E. Again, there is a theorem in vector calculus, which is similar to the first one. Actually, that gives you this one. This one is called, forgot his name. They're a bunch of Green's theorem. That's basically what they're called, but it has a different one, okay? And actually, if we have time, maybe down the road, we can prove them. The proof in physics is not that hard. It doesn't involve a lot of complicated stuff, okay? As long as you take your geometry, your path, and you connect it, first of all, make a secondary path that passes through the first path, basically, and argue that the sum of the two paths is the original path. Then you keep on doing this until at the end you end up with a small area dx dy in the xy plane, but also it could be dy dz, and that is how you pull out all of those partial derivatives, and you end up with basically the curl. The curl, by the way, is a similar way. So remember, I used already a couple of times this this vector in here, gradient, and the gradient in this case is the same operator we defined a long time ago. So gradient is a vector in Cartesian coordinates, takes the derivative with respect to x in the I hat direction, plus takes the derivative, partial derivative in the y direction, and plus takes the z derivative in the z direction. So plug in any vector in here to it, and it's going to give you a dot product, or cross it with another vector. It's going to be a cross product, and dot it with a, put next to a function like this one, scalar function, and you end up with a vector. This is a scalar function for the potential. So it's the same stuff that we discovered a long time ago. So, but this is in Cartesian coordinates. It changes form in other coordinate systems, okay? Anyway, so this is this Faraday's law, Faraday Lens Law. This is the last law that we discovered. Let's talk about Ampere's law, because there is something wrong with it, and we will find how to fix it, okay? And it was actually Mr. Maxwell himself who, this work is due to Mr. Maxwell. He was trying to put everything together, all of the things that we learned together. So Mr. Maxwell, when he looked to this expression, remember Faraday's law, Ampere's law, the way we discovered it was the circulation of the magnetic field over a path, any path, is equal to mu naught times I enclosed by the path. So when I say the path in this case, it's the same path that you choose in here, okay? So now it doesn't become any path, that specific path that we're talking about. So this is Ampere's law. Mr. Maxwell, when he was putting this one, he made an argument that this is not correct. Let's look at it the way, why it is. If I take a capacitor, okay? Capacitor, that is building charge. So right now the charge in it is Q, and there is a current that is building up I, so that I is equal to dq over dt. Okay, so this is the rate at which the charge is being deposited on this capacitor. Of course, from this side it's a negative Q. Okay, and it's the same current. Okay, so this is the same I, but it's moving in the opposite direction. Okay, away from the charge. Anyway. So he said, okay, I'm going to make, we're going to try to apply Ampere's law for this loop, okay? So he chose this loop. Of course, it's a theoretical loop, okay? And he wants to find the magnetic field in a point around it. So this is a circle of a given radius r, and he wants to find the magnetic field in this point, okay? Obviously, Ampere's law in this case, the current is flowing this way, the magnetic field is coming from there. So Ampere's law says this B then, okay, is given by that expression, the one that we just discovered. The circulation of B over this circle, which is just B times 2 pi r, where r is this distance. So it's B times 2 pi r is equal to mu naught times I, and I is this current. Okay, that's good, because that's the I that crosses this area. So this is the area that you can choose. Okay, no problem. We have no problem at this point. Okay, if you blow on that surface and keep the ring the same, so the magnetic field should not change. So this side should not change at all for this area. So it's the same side, but this is the area now we're taking, okay? It's an inflated version of the first one. So on one side, B times 2 pi r, that doesn't change. The reason why it doesn't change is because you are still enclosing that path with the new area. But on the other side, it's going to be mu naught times I that passes through this area. This is the I that crosses that area, which is the same I, because it's the same wire. So there is no problem for this area. Okay. Blow further on it, and end up with this area. So it's going to look like this. And it's the same path, by the way. Like a soap bubble, you know, those bubbles that you form. So they can keep on growing. So now you have a problem. Let's see why. From one side, the path did not change. So the path is still the same. So it's still the same thing, B times 2 pi r. On the other side, it's mu naught crossed with this area. Remember, this is an inflated, okay? There is no wire that crosses this one. So on the other side, it's 0. And that is the essence of the inconsistency in this law. That is the problem with this law. As a matter of fact, if you continue blowing on this until you get it into even a bigger area, which is, let me find another color, which is this area, you're back in business, because now this area will have that same current flowing in this direction. So you're back in business. If you consider the last area where B times 2 pi r, that did not change at all. It's the same path. And now equal to mu naught times the I, and it's the I now that is coming from the other side of the capacitor. So there is no problem in here. It's mu naught I. This is the problem. In between the capacitor, we have a disaster before us. So Mr. Maxwell thought hard and said, okay, there is no current true in here. So no current in here, period. We know that, okay? But there is definitely something changing in here. As Q is piling up through here, the voltage is increasing on this side, okay? So this is V1 and this is V2. In other words, V2 minus V1, V1 minus V2, I'm sorry, is increasing. If the current is actually moving in that direction. If it's the opposite, then it's decreasing, and you take everything in negative sign. So this voltage is increasing. So this V now is going up, okay? And the charge itself, Q, which is equal to C times V, is actually increasing. And there is an electric field now that points in this direction, E. That too is increasing because there is more voltage on this side, okay? So that is time dependent. So he said in that region, I'm going to do the following. I'm going to argue that there is a current. He called it the displacement current. And this displacement current is exactly what I need to make this equation work, okay? So that I have the same I in here. So in this side in here, he said, okay, what I'm going to do in here, I'm going to say this is a mu naught times the same dq over dt that we all know and love, which is I, okay? because that's changing actually in the capacitor itself. And dq over dt for the capacitor, q, remember, it's equal to cv. So this is d with respect to time of c times v. Okay. C, if you guys remember from way back, is equal to the capacitance, and the capacitance is epsilon naught times A over D, and times the voltage. The voltage is just E times D. So that is the voltage across this capacitor, because the capacitor has a nice geometry. The D cancels the D, okay? And the E times A is the electric field in this region times this area. Okay, in that region, and that is actually the flux of the electric field. So he was saying in here, this expression looks like this. It's mu naught times the derivative with respect to time of epsilon naught, the flux of the electric field. Epsilon naught comes out of this integral, this derivative, I'm sorry, it's constant. And then now you have the flux of the electric field. So he called this current the displacement current. You see, he did not completely abandon, and that's what physicists do usually. When they see something wrong with a law, like this one that's clearly wrong, then you try to correct it and see if it works. And if you just add this term, now you're back in business. Because in here, you don't have a displacement current. You don't, there is no electric field changing, so you don't have a problem. So you apply the first term from Ampere's law. Now in here, you don't have current because you don't have really a wire. So you add to it what Maxwell added, and you're back in business, the one that is due to the electric field. So now, empowered with that, this is how Ampere's law now looks like in terms of what we know. So the first one is, again, the circulation of the magnetic field over any path. This is any path. Is the sum of mu naught times the current, the old current, traditional current that is running actually through wires, plus this displacement current, which is just the derivative with respect to time of the flux now of the magnetic field, I'm sorry, of the electric field in that region of space. This is what the flux is. I mean, for this case, it's E times A. E times A will give me the flux because A is a uniform shape and E is constant. That's why E times A is the flux. But in general, it could be more complicated than that. So you take just the integral over whatever area that you're considering. And if the magnetic, the electric field is changing, you do that. So this law now became known as Ampere. I'm sorry, it's capital A. Ampere Maxwell Law. So now we have another law that is, we can write it in this form in here. So this is the displacement current, okay? Actually, Mr. Maxwell actually imagined that there's some sort of a current flowing, but there is none, okay? It has to do only with the changing electric field. So let's put this thing into, again, similar to what we did with the previous equations using basically Green's theorem, and Stokes' theorem is the other theorem that I just remembered, okay? And we're in business, okay? So the integral in here, the curl, is going to just involve the curl of B. So this is the curl of B is equal to mu naught. This becomes just the current density. This is a vector, by the way, plus mu naught times epsilon naught times the partial derivative of E with respect to time. And you strip it of all of the integrals. So those are the so-called Maxwell's equations. We have equation, let's start numbering them. Or actually, let me write them also, all of them in the same place, okay? So this is a summary of the summary. F equals to ma, this is Newton's law. F equals to Q times E plus Q times V cross B. This is Lorentz force. This is Newton. Okay. What else? We're gonna write them all in one form, okay? And then probably we'll write them in the other form. This Gauss's law gives me the flux of the electric field equals to Q over A, Q over epsilon naught, Q enclosed, that is, okay? Not the same Q as the other one, so this is Q enclosed, okay? Gauss's law for the magnetic field is the easiest one of them all, because this is 0, okay? There are no monopoles. So, and this is Gauss's law, because we're giving them names now. This is Newton, this is Lorentz, this is Gauss. This is also Gauss's law, but it's usually referred to as no monopoles. Okay. Now, Ampere's law, which we're going to put it in proper order now back, because Ampere Maxwell now, since we have discovered the correction to it. Where's my mouse now? It says that the circulation of the magnetic field over any closed path is equal to mu naught times the current enclosed. The currents create magnetic field, basically, plus displacement current, if there is any, okay, of the electric field dA, I'm sorry, okay? So this is Ampere Maxwell, okay? And finally, Faraday Lens Law, which gives me the last part of it, which is just the circulation of the electric field now, dl, is simply minus the rate at which the flux of the magnetic field BdA is changing with time, okay? So this is Faraday Lens Law. All of these equations now, at least from Lorentz force down, they are known as Maxwell's equations. And they are, first of all, Newton's laws, you have 3 equations, because this is a vector relationship, and you have it in the x, y, z components in the Cartesian coordinate system. This is also 3 equations, okay? So for a total of 6. This is a scalar equation. It's only one equation, okay? This is actually a scalar equation. It's only one equation. This 2 also have the vector equations, so there are 3 of them in here. So total of 3 plus 3, that's 6, plus 2, that's 8, plus 6, that's 14 equation that you really have to solve on any computer trying to get to it. Now, this is the form that I gave you, the vector form. In the differential form, again, using Stokes' theorem and Green's theorem and all of the others, the divergence theorem for Gauss's law becomes simply the divergence of the electric field equals to rho over epsilon naught. The divergence of the magnetic field becomes just 0 because there are no monopoles. So this is Gauss's law for both, okay? And then Ampere Maxwell's law becomes simply equal to the curl of E, curl of B, I'm sorry, is equal to mu naught times the current density plus mu naught times epsilon naught times the rate at which the electric field is changing with time. And finally, Faraday Lens law giving me the curl of E, which is equal to minus the derivative of B with respect to time. Again, they are the same number of equations. Here I have 1, 2, plus 3, that's 6. That's 5, plus 3, that's 8. But don't forget you have 6 more in terms of Lorentz force and in terms of also Newton's laws. This is a summary of everything that we know in terms of electricity and magnetism. Mr. Feynman, when he gets to this point, he says this is the summary of everything we know. As a matter of fact, it is. Everything you've learned so far in physics can be put into this simple equations. F equals to ma summarizes everything you learned in physics 4a. Okay, and there are 3 equations because you have 3. There are 3 components. Physics 4b adds to them this bunch of equations, okay? The 11 other equations. So if you know these things, technically you can pass anything in physics 4a and physics 4b, end of the story, okay? So this is in a nutshell everything that you know so far in physics, okay? So if anybody asks you what do you know in physics, give him these equations: Newton's law, Lorentz force, the 4 equations of Maxwell, namely the first one is Gauss's law for the electric field, Gauss's law for the magnetic field, which is the easiest of all of them, okay? Because it's the, basically it says the divergence of the magnetic field is 0, the magnetic field never diverges. And then Ampere Maxwell's law, okay, which gives you how the magnetic field basically circulates, okay, how it's created, okay? And then the last one is the Faraday Lens Law, which gives you how the electric field actually circulates, because that's a weird one. According to this law, it should not circulate at all. According to this expression, this one, since it derives of a potential, it should not circulate. Okay, its divergence is something, but the circulation of this one is going to be zero. Let me tell you why this is prohibits that circulation. Okay, because if I want to find the circulation of E, I'm going to cross E. I'm going to basically cross this term with itself. Okay, this is parallel to the divergence. This is perpendicular to, I'm sorry, this is, what should I say? It's going to involve the sine of 0 degrees at some point. Okay, there is actually circulation in here that you're going to have. So I'm trying to think of a way of explaining it in here without really doing a lot of explanations. Here is the point. The electric field in here is always diverging. It's leaving. So this expression doesn't tell me that the electric field should circulate. Yet this expression gives me circulation of the electric field, and that is something kind of strange. And the reason why there is a remedy to it is because this electric field is actually non-conservative. Non-conservative meaning it does not really derive of a potential. Does not derive of a potential. Okay? Which means technically we should not use Kirchhoff's rules for it. We should not use the law for the second rule, especially for the, we know the conservation of charge is going to work, but that of the voltage should not work because there is no potential that I can write for this expression here when I'm dealing with the AC currents. And we're going to get into this discussion on how to basically overcome this difficulty, because this is really a problem for a physicist and engineer doesn't care about the argument whatsoever. Okay, but for a physicist, you really need to walk on a fine, basically, argument to argue why you can use Kirchhoff's rules in there, so that you can use AC circuits. And all of the circuits are AC circuits. For the vast majority of them are AC circuits, basically. So that you can justify it, and from there on, you're going to say, okay, we're good now, so that we can continue working with these things. Okay. So that is something that we have to do. Before we do that, we are going to introduce the inductor in chapter 30, and then from there we're going to continue and build circuits that involve inductors, capacitors, and resistors, the so-called analog circuits, and that's where we'll find the problem. That is exactly where we're going to run into the difficulty, at least conceptually, and hopefully we can resolve it conceptually so that we can use Kirchhoff's rules, or a modified version of Kirchhoff's rules, so that we can do circuits there. So this is, in a nutshell, what this chapter is about in terms of the concepts that are actually tested. Namely, the two concepts I had to cover were these two. I'm not going to delve a lot, honestly, into the, this is item 29.7, the last one we discovered, basically, into superconductors, because superconductors, they have a weird behavior. Yes, they're it's below a certain critical temperature. Their resistance drops to 0, so they become basically perfect conductors, but they have also weird behavior when it comes to magnetism. They start to repel, according to the Meissner effect, the magnetic field, and there is no magnetic, so the magnetic field will go around them. So if you put them inside a magnet and that magnetic field is not strong enough, so the magnetic field will go around them, and you can use them for levitation, actually, because they behave as if they are magnets. Now, if the magnetic field is too strong, actually the magnetic field can destroy the superconductivity, and the material becomes a normal material again. So this is the last item in there, and it's not, like I said, testable in terms of concepts that you're going to have an exam on or anything like that. But at least it's good to know, especially if we're going to go into material science or solid state physics, that there is something called the Meissner effect in there, where the magnetic field is actually expelled, similar to how the electric field is actually expelled from a conductor. But this one is superconductor. The physics of it is really involves other concepts that we're not going to get into them in here. But this is something in here for chapter 29.8. The reason why I'm trying to also get something else in here is this problem, because I promised you guys to have this problem done for you. Any questions, first of all, about the two things that we did? Okay, before I ask you any questions. The deal I did about the summary of everything we did, okay, so far. It is very important that you guys need to know it, okay? This is actually the objective, one of the objectives of this class, that you need to know at least the 4 equations of Maxwell. The first one is Gauss's law, where the divergence of the electric field is just proportional to the charge enclosed, 1 over epsilon naught there, the term in there. The second law is the Gauss's law for the magnetic field, which is 0, and that's the easiest thing that you can remember. The third law of basically from the Maxwell's equations is so-called Ampere Maxwell's law, and that is the one that gives me the magnetic field. The magnetic field is produced by electrical charges, by the electrical currents, and but in places where there is no electric currents, where the electric field changes, also it can produce a magnetic field. Okay. Also, the last law, the magnetic field, if you wish, there is an EMF if I change either the electric field, the magnetic field, or change the area. The flux of the magnetic field would give me basically an EMF in this case. The EMF has a signature of a non-diverging but circulating current, circulating magnetic electric field in this case. So those are the concepts in here. If we have time, and I don't know if we are, honestly, we're going to discuss. We discussed the cyclotron, which is a nuclear accelerator, way back when we did the stuff. I don't remember exactly when we did when we introduced the magnetic field first. Okay. Now, since the magnetic field can vary in time and we can do things with it, there is another concept that is called the betatron, which is a different kind of nuclear accelerator that uses actually the fact that the magnetic field is used for 2 purposes. First of all, to confine your accelerating materials, protons, for example, to keep them in space, because that's what the magnetic field will do. It always will circulate it, cannot, because that's the cyclotron, basically. The ratio of the velocity of the radius is fixed. So no matter how fast it is, V over R is fixed as long as everything else is fixed on the other one. So that omega is fixed, okay? That is one property. The other thing that you do also, you accelerate the particles with the magnetic field by changing it with time. So it's going to create a circulating electric field, and that circulating electric field will give the protons or the electrons, whatever you're trying to accelerate, faster and faster. You need the charged particles. You cannot do it for neutrons, of course. So they can move faster and faster as long as you keep on changing the magnetic field. Okay, if the magnetic field is changed, the particles are confined first. They cannot move. They cannot have a bigger radius and fly on you. Okay. And the other thing, because the magnetic field will force them to stay in that region, circular, okay? And then when you vary it, it's going to create an electric field, and that electric field will make them circulate in that region, and they can reach tremendous velocities, okay? And that is basically where you have to be very cautious with those problems, with the betatron, whether or not you will be able to accelerate it past beyond a point where it's going to be relativistic effects. The only limitations for this betatron is actually the fact that the particles, because they are charged and they start to moving faster and faster and faster, they will accelerate and start radiating energy. So that is the limitation of it. So probably we'll do that maybe at some later time or a part of a homework or some other assignment. Anyway, problem 59. And like I said, it's very, very important to remember this Maxwell's equations. So that's the question of the day. Please go and review Maxwell's equations, all 4 of them, okay? I know I mentioned 2 other equations in Newton's law of second law of motion, and also Lorentz force, and Lorentz force is critical for this one. It's the link between the 2, okay? Do you guys understand the task? To go and review all 4 equations, because we need them down the road. Yes? Okay, thank you, Daniel. Okay, so I'm going to continue now with this problem. So problem 59 gives you a rod, okay, 24 centimeters long, rotates with an angular speed of 8.8 radians per second, okay, at about an axis through one end of the perpendicular to the rod. So basically in this problem, okay, that's not good. So I took the center of rotation in here in the bottom for the rod, okay? And I'm assuming that it's actually going clockwise, which is a bad idea because this is a negative direction for the angles, okay? So this is omega, which is 8.8 radians per second. Okay. The rod itself has a length of 24 centimeters or 0.24 meters. And what else do we know? The plane rotates about the rod of the perpendicular to it in a magnetic field of 0.65 Teslas. This is a big magnetic field, super strong, okay? Now, what is the induced EMF in the rod? Here is a question here. They didn't give me any directions. So since I took this one in the negative direction, so I took also the magnetic field is pointing inward. So the magnetic field is pointing into the screen, okay? You can choose it however you want to, but you have to be careful with your mathematics. So according to my notations, V is a minus R omega theta hat. Okay, in polar coordinates, this is the x-axis, this is the y-axis, this is theta, okay? This is R hat. This will be theta hat, okay? Obviously, this is negative, and it's R omega for a point in space. So I took a point R from my on the rod, and I found its velocity. Okay, as long as it's moving with a constant omega, then this is its velocity, and it's again negative. Okay, and I also know I took B to be negative. That's to compensate for my earlier mistake. If I take them both positive, it's going to be the same result, okay? If I take one positive and the other one negative, it doesn't matter. It's going to give me the same physics, but probably it's going to spin in the opposite direction, okay, if it's going to spin, okay? So it's fine, okay? So you can take whatever directions because they didn't give you that. So this is B, okay? Now, I have to be careful with R because the vector R in this case, it's a vector, which is just R times R hat. When I take its dr, I'm just moving along the rod in here. So I don't care about theta hat because of the fact that I'm not actually trying to integrate only across the rod, because that's basically what they're trying to do in here, trying to find the circulation in this case of the across this element in here. So for right now, ignore this part. Okay, it's going to be needed later on when I apply basically when I try to find the work in this case, okay? So the force now, a single charge. Remember, Ampere's law, Lorentz force is Q times V cross B, but I'm interested only in unit charge, meaning that I am interested in 1 Coulomb charge, okay? Just do the cross product. Remember, I'm using R hat, theta hat, and Z hat is coming out of this picture because R hat is along the rod, theta hat is perpendicular, and Z hat is supposed to be coming out of it, or K hat if you wish. But K hat now, I took the magnetic field inward, so everything is going to be given by that expression. And if I do the cross product correctly, this is the expression that I will find. BR omega times R hat. I'm trying to find the work needed, okay, for that charge, for the unit charge to move a dr distance, okay, along the rod. Of course, the charge is not going to fly out, because if the charge flies out, we have a problem. That's why this differential form in here, I don't care about the angular displacement, because the charge is moving in here, okay, along the rod, along the radial direction only. So if the charge is moving distance dr, this is the displacement for it. So the force in this case times displacement gives me the work. And the work per unit charge is what we call the EMF. That's why I'm using this epsilon in here. So the epsilon in here is the work per unit charge, okay, per 1 Coulomb. And that is by definition what the EMF is. So if I multiply this vector now with this dr, and the dr has R hat times R hat, and R hat times R hat is a unit vector, so it's 1. So I'm left with BR dr. This is the expression that I'm left with for the work to move 1 Coulomb distance dr. But if I want to move it from 0 to L, I need to integrate this expression, and this is basically the EMF for the entire rod that establishes itself for the entire rod. So basically, when you spin it in a magnetic field, charges, positive charges, they start to move and leave a negative side in here, and they pile up on the other side, okay? So this will become a positive, and this will become a negative. This becomes a battery. As long as I don't connect it with any other wire or resistor or anything like that. This is my circuit, basically. Okay? If I connect it, then the current starts to flow. But I need to deposit charges on the other side. You and I know that the situation actually in reverse, because the only thing that moves are electrons, and electrons will leave this side, leaving positive ions in here, and pile up on the other side, and I have a net deposit of negative charges. It's the same picture. Whether positive charges move from the center of rotation all the way to the end of the other rod, which is fine, okay? But since we know the truth, that's actually the electrons that move from the end of the rod down to where the center of rotation is, then it's the same net effect, basically. I have an EMF now. It's like I have a battery now that looks like this. And this is the EMF that I was able to calculate. I didn't plug in the numbers, but I assume you guys can plug in the numbers, B omega L squared. So we have B, which is 0.65. We have omega, which is 8.8 radians. And we have L, which is 0.24 meters. So it's going to give me a value in here if I plug in all the numbers. I don't know how much, but it should be giving me a value. So what is the induced EMF? So we found it. What is the potential difference between its ends? Okay, this is the potential difference between its ends. Okay, so that's the answer to part B, actually. Okay, and it's induced actually by this expression. So this is actually the induced one. So this is the EMF. So you equate them, and that's it. You're in business. Suppose instead of the rod rotates about an axis through its center and perpendicular to rod. In this case, what is the potential difference between the ends of the rod, between the center of the rod and the end? I'm not going to do a calculation, but I'm going to argue the symmetry to see exactly what's going on. So I have my rod now. And if we do the calculation, it's going to give me the same thing. This is my center of rotation now. It's in the middle. Obviously, charges will start to pile up in here. Positive, okay, depleting this region, but also they will start to pile up in the other side too. And in other words, this integral is going to be from negative L over 2 to positive L over 2. And since this is an odd function, it's going to give me 0. So it's the same integral as before, B omega R dr. But the boundaries of integration become from negative L over 2 to positive L over 2. And this should give me R squared over 2 integrated between these two things. So it's going to give me 0. So there will be no potential difference between the two ends, because both of them will be in the same potential in this case. Okay. But there is a definitely potential difference between this end and that end, and this end and the other end. And that's basically is going to be equal to B omega, the integral from 0 to L over 2 of R dr, and this should give me B omega L squared over, what is it, 8? Because I will have an L squared over 4 from the upper limit, but don't forget I have another 1/2 that is coming from the integration of R. So this is this difference in potential. So this will become B omega L squared over 8, and this will also be B omega L squared over 8, okay, this way, and the other one this way, and there is no net. So this will be at the same potential as the other one, and the net potential difference is actually 0, okay? So this is this problem 59. I hope that you guys can go more into details of it and plug in the numbers and see how it works and understand it. Any questions about this problem? Okay, guys, I will see you on, actually, probably I will communicate with you further on the exams once I made up my mind. I hopefully no later than Thursday, no later than tomorrow. You should know the format for it. Most likely it's the same format at both exams, 1 and 2, but it's going to be a little bit less time than the previous exam, okay? So this ends chapter 29, and I will, guys, see you actually the week later, because Wednesday next week there is no class, okay? There is it's a day off. So we're gonna meet the week after. Black Friday, okay. Good luck with that too, okay? See you guys. Thank you. I'm going to stop the recording.